Okay. So we're going to start with lesson 1. And if you remember going back, a case is an experimental unit from which data are collected. And a variable is a characteristic that is measured and can take on different values. And an example of that, if you're having trouble putting it in perspective, is a 3rd grade teacher wants to know if students who spend more time studying at home get higher homework and exam grades. So here in this example, the 3rd grade students are the cases, and our variables are the homework and exam grades, because these are what are measured, and they can each take different values. So moving more into variables, we can have categorical or quantitative variables. So categorical variables are names or labels or categories that they can have a logical order or they can have no logical order. And these are usually qualitative. And then moving into quantitative variables, they're numerical values with magnitudes that can be placed in a meaningful order with consistent intervals. So these are numerical values, and they can either be discrete or continuous. Discrete quantitative variables have a set value. So if you think of, for example, the number of children in a household, that would have a set value, while continuous variable would have a value between values, such as weight or distance you run. So you could weigh 125.2 pounds, for example. That would be a continuous variable, while discrete variable would, if you think of more like if you're counting children per household, it could be 1, 2, 3. You can't have values between values there. So moving more into the difference between explanatory and response variables. Explanatory variables are also known as independent variables. They explain variations in the response variable in experimental study. So these are what are being manipulated. While the response variables, we call that a dependent variable as well. The outcome that is measured following the manipulation of the explanatory variable. So we always measure the response variable. So going back to that example from before, how does the hours spent studying affect your exam grade? So we want to manipulate our hours spent studying, which is our explanatory variable, and measure how that affects our exam grade, which is our response variable. So I know I have gotten a lot of questions about population parameter, sample statistic, and mean proportion and correlation are the most common ones I've seen so far. But these are just the symbols and when you use them. So I just want to make sure I go over that for the midterm. It's very, very, very important to know. Population parameters are used when you're speaking in terms of the population as a whole, while sample statistics are used when you're talking about your statistic that you calculated from your sample. And you just want to make sure you know the difference between those and when to use them. So for example, you would use your population parameter when you're writing your null and alternative hypotheses. All right, so simple random sampling is a method of obtaining a sample from a population in which every member of the population has an equal chance of being selected. So this is selected without replacement, which means once we choose our sample, once we choose our sample, there's not a chance of that being selected again. While convenience sampling is less preferred here in statistics, because it's when you obtain a sample from a population by ease of accessibility. So this means that our sample is not random, and therefore it's probably not representative of the intended population, which is not what we want out of our samples. We want to make sure that A is random and B can be representative of the population as a whole. So I'm going to go over non-response and response bias. So non-response bias is favoring certain outcomes that occur when the individuals who choose to participate in a study differ from the individuals who choose not to participate. So an example here I have from a restaurant. A restaurant invited their recent customers to complete an online survey. Customers who had very strong feelings about their experience, either positive or negative, were very likely to complete the survey, while customers who had a neutral experience were much less likely to complete the survey. So if you think about it in this perspective, customers who had a great time at the restaurant were probably very motivated to write to answer the survey so that other people could hear about the restaurant or they could keep coming. Or if you had a very negative experience, you could want to communicate that with the restaurant as well. But if you had a neutral time, you may not feel motivated at all to write, to respond to that survey, but you want all of your customers to respond because you want a balanced level of feedback that is representative of your population of customers. So that's non-response bias. Response bias, I think personally that's a little bit more clear. It's when you favor certain outcomes that occur when participants do not respond truthfully. So this may align with social norms or to appease the researcher. So response bias is really just about the way you respond to the researcher who's asking. So I like to think about if a teacher collected a survey from her students asking if they've ever cheated on a quiz, if the students did cheat, they probably would not admit to that. They would probably lie about cheating if they did, because you wouldn't want to tell your teacher that you cheated, because you would most likely get in trouble, or your teacher just wouldn't like you if she knew that you had past of cheating. So that's response bias, is when you're not responding truthfully to a situation. So experimental and observational studies are also important to know. Experimental studies are studies in which the researcher manipulates the treatments received by the subjects. So this is also called a scientific study. And then observational is a study in which the researcher collects data without any manipulation. So this is entirely left to nature. It's a non-experimental study. The treatments are not manipulated in any way. One problem with observational studies is that they do not take confounding variables into account. So confounding variables are also called third or lurking variables. They can vary between cases, and they're related to both the explanatory and response variables. So a common confounding variable you may hear might be age. Age may not be taken into account in some observational studies. So just something to look out for. All right, so now we're going to go over independent and paired groups. So first with independent groups are cases in each group that are unrelated to one another. So if a t-shirt company studies how many t-shirts American men and women own, they take a random sample of 1,000 American adults and ask each individual if they identify as a man or woman and how many t-shirts they own. So here in this sample, they're independent groups because the number of t-shirts a man owns does not affect the number of t-shirts a woman owns. While in paired groups, they're also called dependent samples or matched pairs. This is when cases in each group are in some way matched with one another. So, for example, if your teacher wants to compare student scores on the midterm and final exam, so your scores from each exam are paired to yourself. So she obtains a sample of students and records each student's midterm exam score and the final exam score. So this is an example of a before and after paired group. All right, so blinding is used to avoid bias. So we have single blind and we have double blind. So first with single blind, a single blind study is a research study in which the participants do not know the treatment that they have been assigned to. But in a single blind study, the researchers do know the treatment that the participants are assigned to. While in a double-blind study, neither the participants nor the researchers know which case is assigned to each treatment. And also, there's a control group. That is when you have an experimental condition that does not receive the actual treatment. So it is a group that stays the same, so you can compare it to the group that is receiving the actual treatment. So this control group may receive a placebo, or they may receive nothing at all. If you need a refresher on what a placebo is something that appears to the participants to be an active treatment, but it doesn't actually contain the active treatment. So if the researchers are giving out pills to their participants, they will give the pill with active treatment to the participants who are getting the treatment, and they will give maybe, for example, a sugar pill to the control group so that they think that they're actually participating in the study, but they are participating in the study, but they're not actually receiving the active treatment. Okay, so that was a lot, but we're going to do our first review. A school psychologist wants to use students' intelligence test scores to predict their reading comprehension scores. She takes a sample of 100 students and records each individual's intelligence test and reading comprehension scores. In this scenario, what is the explanatory variable? So again, if you didn't hear before, you can just type your answer into the chat box. I'm going to go over it in a couple minutes. All right, awesome. Everybody answered, and the answer is B. You guys got it right. So just to go over a quick review, the intelligence test scores is the explanatory variable here because this is what is being used to predict the response variable, which is the reading comprehension scores. All right, review 2. Which of the following is not a quantitative variable? Awesome. D is our answer here. Weight, children per household, and running distance, all quantitative variables. D, favorite ice cream flavor, is a categorical variable. All right, we're moving on to lesson 2. So we're going to start with one categorical variable. So data concerning one categorical variable is summarized using a proportion. So you definitely know what a proportion is by now. A proportion is a number in the category divided by the total number. So the symbol for proportion is p hat, and the symbol for your population proportion is p, lowercase p. So the way you calculate p proportion in terms of the sample is x over n. So it's your number in your sample divided by the total sample size. And just remember, you guys probably are aware of this by now since you've been so familiar with proportions, but a proportion must be between 0 and 1.0. All right, so now we're going into risk and odds now. Okay, so risk and odds. So we're going to start with risk. So risk is the probability that an event will occur. So you can calculate risk by taking the number with the outcome divided by the total number of outcomes. So if we start with an example of flu risk, if we say 45 out of 100 children get the flu each year, we can calculate the risk of getting the flu to be 45, which is the number of children who get the flu, divided by 100, which is the total number of children. And we can say that 45% of children get the flu each year. Now, if we compare that to odds, odds is the likelihood of an event happening with the likelihood that an event will not happen. So risk and odds have the same numerator, but they have different denominators. So odds just compares the number in the other group, so it's the number without the outcome in the denominator. Or you can calculate odds by taking, if you've calculated risk previously, you can take risk and divide that by 1 minus risk, and that will give you your odds. So since we calculated flu risk for the previous example, we can calculate our odds using the second formula. So we can do that by taking 0.45 divided by 1 minus 0.45, and we can get 0.818. So we can say that the odds of a child getting the flu is 0.818 to 1. Okay, so here's some visual representations you guys have got familiarized with throughout the semester so far. And I'm just using the Penn State Math Club for an example. I made up these numbers, but And you see in the pie chart on the left, it shows age as the whole, and you can see each section represents a different age, and you can see that the majority members here is 21-year-olds in the dark gray. You can also see the frequency table has the numbers broken down a bit, so you can tell more clearly what the count is and the percentage of each member. So it shows the same data in each, but it has a little different representation of the majority and the specific numbers in each group. And then you can use a bar chart, which is similar. It just puts it in a different perspective of seeing the data, but it's the same data. All right, so two categorical variables, you can use a two-way table. So here our two categorical variables are gender and class standing. So you can see each class standing is broken down by males and females, and you have the total. All right, so moving on to probability. So the probability is the probability that event, quote, A will occur. So we can calculate it by the number in group A divided by the total number. So just make sure you know that the range of possible probabilities is between 0 and 1. It's very similar to proportion. So the probability of an impossible event would be 0. So if you get a probability of 0, that means that this event cannot happen. It's impossible. On the other hand, if you get a probability of 1, that makes that event certain to happen. So an example for 0 probability is if you say the probability of rolling an 8 on a 6-sided die. That's impossible. So that would have a probability of 0. Okay, so disjoint independent events. So disjoint events are events that will never occur at the same time, so they're mutually exclusive. For example, if you're comparing class standing, you can be a freshman one year and a sophomore the next year, but you'll never be a freshman and a sophomore at the same time. That's just exclusive. A Venn diagram is a visual representation in which the sample space that is drawn on the right is depicted as a box, and each event, so we have events A and B, are represented as circles within the sample space. So in that box there, A and B are each events that happen, and the sample space is the box surrounding it. And then independent events, we kind of went over that before, but independent events are unrelated, so the outcome of one event does not affect the outcome of another event. Okay, so combination of events. So intersection, first, is the probability of A and B occurring. So both of them have to occur for an intersection, while in union, it's the probability of A or B. So we could have A happen, or we could have just B happen, but we could also have A and B happening in a union as well. Complement is the probability of not A occurring. And then conditional is the probability of A given B. So something must, so for example, here in conditional, B must happen for A to happen as well. All right, so outliers are one or more observations within a set of data that may fall outside the general scope of the other observations. So you can identify outliers by looking at a dot plot, box plot, or a histogram. So here we have a dot plot, and you can see that the outlier here is past 72, so I would say that would be around 75 on our dot plot, and that's just very clear that it is outside the general scope of the other observations. And you should typically be able to identify outliers very clearly. So shape is something that's very important. So you have, here we have symmetrical distribution and we have a normal distribution. So on the left, our symmetrical distribution is similar on both sides of the center. And then our normal distribution on the right is a type of a symmetrical distribution, but it's more bell-shaped. So our normal distribution will have a mean of 0 and a standard deviation of 1. So moving into skewness, this is when you don't have a completely symmetrical graph. Some of the times you'll have a skewed distribution. So a distribution is considered skewed if the values are spread out on one side of the center than on the other. So starting on the left, there's a left skewed distribution, and a left skewed distribution occurs when a lot of the data piles up on the right side, So it leaves less data on the left side, so we call it left skewed. And then just the opposite on the right, we have a right skewed distribution. A lot of the data seems to be piled up on the left side of the distribution, and there's less on the right side, so that's a right skewed. All right, so we have three measures of central tendency that we're going to use. We have mean, median, and mode. The mean is the average, so it's calculated as the sum of all the data values divided by the number of the values. So we call our sample mean our x bar, and then we have a population mean of mu. Next, going on to our median. The median is the middle of the distribution that has been ordered from smallest to largest. So you want to make sure that in order to find your median, you order your values from smallest to largest. For distributions with an even number of values, you'll take the two middle values and find the mean of those. So you would just add them together and divide by 2. Lastly, the mode is the most frequently occurring value in the distribution. So you could have more than one, but it can be used with quantitative and categorical variables as well. So mean, median, and mode can affect, skewness can affect mean, median, and mode. So typically in a symmetrical distribution, your mean, median, and your mode will all be equal. But once you have a left skewed distribution, your mean will be less than your median, and your median will be less than your mode. And then switching to a right skewed distribution, your mode will be less than your median, and your median will be less than your mean. So I thought that was just something good to know. And then the empirical rule. Your empirical rule is a statement about normal distributions. So it's the shortened version of it is also called a 95% rule. So the 95% rule states that approximately 95% of the observations fall within 2 standard deviations of the mean. So you can see in the distribution drawn on the right, the 95% of the data falls within 2 standard deviations of that mean of that normal distribution there. And then the empirical rule just talks about how 68% of the data will be within 1 standard deviation of the mean. It adds in the 95% rule and then states that 99% of data will be within 3 standard deviations of the mean. So the empirical rule is really just summarized by that plot there on the right. Okay, so z-scores are used to describe one observation in relation to the distribution of all observations. So you can calculate your z-score by taking your original data value, subtracting the mean of the original distribution, and then dividing that by the standard deviation of the original distribution. So I think next we have in our review, you can calculate the z-score. Yeah. So the average weight of a female border collie is 45 pounds with a standard deviation of 4 pounds. What is the z-score for a female border collie that weighs 51 pounds? All right, awesome. So everybody got B there. So just going over it, you take your x of 51 and subtract 45, which is your x bar here. And then we divide that by our standard deviation, which is 4, and we get 1.5 as our answer. All right, so moving on to the next. Okay, so percentiles here is the proportion of a distribution less than a given value. So if we put this in terms of an example about test scores, so if a student scores in the 90th percentile on a test, then he or she scored better than 90% of the students who took the test. So in that 90th percentile, out of all the students who took the test, he or she did better than 90% of the students. So that's very good. So 5-number summary has 5 numbers, your minimum, Q1, median, Q3, and your max. So Q1 is the first quartile, which is the 25th percentile. Q3 is the third quartile, and that's the 75th percentile. Your range is the difference between the maximum and the minimum. So you subtract the maximum, you subtract maximum minus the minimum to get your range, and then to get your IQR, which is your interquartile range, you can subtract Q3 minus Q1. And that's what we're going to do here. So a teacher wants to examine students' test scores. The 5-number summary for their scores is 74, 80, 89, 90, and 98. According to the 5-number summary, what is the IQR? All right, awesome. So our answer here is 10. So for our IQR, so Q3 is our 4th number in the 5-number summary, which is 90. And then Q1 is our 2nd number, which is 80. And to get the IQR, we just subtract the 2, and our answer is 10. So moving on to lesson 3. So here I just put an example of a single box plot, and it shows some of the most common things you'll see on a box plot. So just starting from the top, I'll just walk you through what I see here. So at the top, you see the little star, the asterisk. Those represent outliers. So you see 1 on the top and you see 2 on the bottom. So those are outliers. Then moving down to the first whisker here, you see the largest value that is not an outlier. So our outlier would technically be our maximum, but this is the largest value that is not an outlier. Moving down here to the first line, this is our third quartile, Q3. And then moving down to the middle, here is our median of the box. And then on the first line of the box, you have Q1. And then moving down the whisker, it's similar to the top. You have the smallest value that is not an outlier on the bottom of the whisker. And then we have 2 more outliers down there. So there's a way we can identify outliers if we're just given a set of data. And we can do that by calculating a lower fence and an upper fence. So we calculate our lower fence by taking Q1 minus 1.5 times IQR. And then we can calculate our upper fence by taking Q3 plus 1.5 times IQR. So we can determine if we have outliers after calculating these 2 fences by saying that any observation below the lower fence or above the upper fence is considered an outlier. So a teacher wants to examine test scores. Their test scores are below. You see that they're in range from smallest to largest. So you see that B here represents the 5-number summary, so 74, 80, 89, and 90. And we're just going to calculate the lower and upper fences for this 5-number summary here. So we can calculate an IQR by taking 90 minus 80. We get 10 as our IQR. And we can calculate our lower fence by taking Q1, which is 80, subtracting 1.5 times our IQR of 10, and we get 65 as our lower fence. Then we go to calculate our upper fence. We can take 90, which is Q3, and add 1.5 times 10, and we get 105 as our upper fence. So now that we have our lower and upper fence, any scores below the lower fence of 65 and above the upper fence of 105 are considered outliers. So looking at this data set, are there any outliers present? All right, awesome. So no, there are no outliers present here because since the data was actually given in numerical order, you can see that the lowest number is 74 and the highest is 95, so there are no outliers. All right. So we're going to start talking about scatter plots now. And scatter plots are used to show the relationship between the explanatory and the response variables. So in a scatter plot, the explanatory variable would be on the x-axis and the response variable will be on the y-axis. So just some things to consider when you're examining a scatter plot. Your direction, is it going in the positive or negative direction? Is it linear or nonlinear? What is the strength between the two variables? And are there any outliers present? All right, so we're going to talk about correlation for a little bit. So correlation is the measure of the direction and strength of the relationship between two variables. So correlation varies between mean and proportion in that it shows it really doesn't have a unit to it, and it's really just showing the strength of the relationship between two variables. So it represents strength and direction between two variables. So you have in your symbols for correlation, we have a sample symbol of an R, lowercase r, and our population symbol is a rho. So just some things to know about correlation at the bottom here. Your correlation will range from -1 to +1. If your correlation is greater than 0, that means you have a positive association. If your correlation is less than 0, that means you have a negative association. The closer your correlation is to 0, that means the weaker your relationship is. So it doesn't matter whether it's positive or negative, they will still be positive and negative are more equal in this case when you're talking about the strength of relationship. So the closer your correlation is to -1 or +1, the stronger your relationship is. And then I already mentioned that correlation doesn't have a unit to it. And then the correlation between x and y equals the correlation between y and x. So it really doesn't make a difference when you're talking about correlation, which variable is x and which variable is referred to as y. So here's just a chart just to give you an idea. You don't have to memorize this by any means, but it's just to give you the idea of the strength of the relationship. This chart would be the exact same if you put a negative in front of each number. So just showing you that how very weak is defined, or moderate, or very strong, just in terms of correlation. Okay, so simple linear regression is when you use a straight line to predict a response variable when you're using one explanatory response variable. Now here, it does matter which variable is x and which variable is y. So to calculate the simple linear regression for a sample, you would take the predicted value of y, and that is equal to your y-intercept plus your slope times your explanatory variable. And you can calculate a residual. A residual is the difference between your observed value and the predicted value. So you can calculate your predicted value, and then you can measure it to compare with how that relates to your observed value to see how close you are to your calculation or your prediction. So this residual really just measures how far away you were, basically, from how far away your observed and your predicted values were. So you calculate that by taking the actual value of y and subtracting the predicted value of y, and that's your residual. Okay, so according to the box plot, which of the following is approximately represented by a score of 505? All right, awesome. Yes, A is our answer here. So we're looking for a score of 505. Q1 represents that first line of the box, and that's around 505. This can't be our minimum because our minimum is the bottom of the whisker around here, and that would be below 500, we can see. And then our median is just the middle line of that box, that blue box, and that's well above 520. So Q1 is our answer here. Okay, which of the following values of R could be used to describe a very strong positive association between two variables? All right, so we have a little mixed reaction to this question. So this question calls for a very strong positive association between two variables. So yes, B has a very strong association, but it's not positive. So A is our answer here because it's positive and strong. B, if it was looking for just a strong association, then that would be our answer. But since we're looking for positive and strong, A is our answer. C is not a contender because that means there's zero relationship at all. Okay, I think that's it. Yeah, so now we're on to lesson 4. So this is all about confidence intervals and getting into sampling distributions as well. So just a definition of a confidence interval, it's a range computed using sample statistics to estimate an unknown population parameter with a stated level of confidence. And then your sampling distribution has sample statistics with a mean approximately equal to the mean in the original distribution, and then your standard deviation, which is known as your standard error as well. Okay, so this is a crazy slide, but this is basically just an introduction to confidence intervals here. So the formula for your confidence interval is at the top. It's your sample statistic plus or minus a margin of error. And then you see that the margin of error is broken down into your multiplier times your standard error. So that is what your margin of error is equal to. You may see the formula written 2 different ways. I usually write it sample statistic plus or minus margin of error, but some people may write it sample statistic plus or minus your multiplier times your standard error, but it's the same thing. The margin of error depends on 2 factors, so it depends on the level of confidence. That determines the multiplier, so whether it's 95%, 99%, 90%, that affects the multiplier that you're going to use. Second, the value of your standard error. That affects how much bigger or smaller your margin of error is, which can affect, in the end, the confidence interval. And then really just the rest of this slide is just more about the empirical rule. So you see that same image there, that was from the empirical rule. And then below it is a chart that just shows some common multipliers that you may see. 68%, this is just summed up from the empirical rule as well with the multipliers that we use. And then the form for a 95% confidence interval, it's the same as the other one, but you're just using 2 as your multiplier because that's the multiplier you use for 95% confidence intervals. Okay, so concluding a confidence interval is very important. In the end, you will typically get an interval of 2 numbers, so it'll be 2 numbers, but it's important to write a concluding statement that interprets that data. So that statement could say, I am a certain level of confidence percentage sure that the population parameter or whatever population you're using is between this number and this number. So that's a common example of a statement. It doesn't have to be the same. A lot of them vary, but they're most likely around the same idea. All right, so bootstrapping. Bootstrapping is a resampling procedure that uses data from one sample in order to generate a sampling distribution by repeatedly taking random samples from the sample. So it's also known as sampling with replacement because each sample has a chance of getting selected again. So I think the best way to go over bootstrapping is just to go through an example. So if we have data concerning the heights of individuals in a random sample of 15 people, to construct a bootstrap distribution for the mean height, we would first randomly select one individual from that sample and record their height. Then, with that individual placed back into the sample, we would randomly select a second individual and record their height. So this is known as sampling with replacement because we put each case back into the sample after recording their height. So a way I like to think about sampling with replacement is if you have a hat and you put each person down on a piece of paper, and then you pick each piece of paper out, record what you get, then you put it back in the hat. It has just an equal amount of being selected again as all the other pieces of paper. That's just an easy way I like to think about it. So once you put it back in the hat, you select another one until you get back to 15 values because that is what is in your original sample. So then you use those 15 values that you selected in order to compute a bootstrap sample mean. And you can repeat that as many times as you want. And just remember that individuals may appear in the bootstrap sample more than once. This slide is really just showing the relationship between sample size and standard error. So they have an inverse relationship with each other. So as your sample size increases, your standard error will decrease. Also, as your sample size decreases, your standard error will increase. So I just illustrated this by these 2 distributions. You see that the first distribution on the left has a smaller sample size than the distribution on the right, and they have a smaller standard error. I can tell this 2 ways. The more clear way is by on the top right corner, you can see the standard error listed, and you can see that it gets smaller as it goes higher up in sample size. But you can also just tell by the variability of the graph. So you can see that the graph is more variable in the one on the left, so that would mean it had a higher standard error. And you can see it's less variable in the graph on the right, so it would have a lower standard error. Okay, well, so we're going into lesson 5 now. And lesson 5 was all about hypothesis testing, so this was taking a little switch from confidence intervals. So hypothesis testing is a more formal method for testing whether a given value is a reasonable value of a population parameter. So you're going to compute the probability that a population would produce a sample statistic as extreme or more extreme to the one we observed in our sample. So we're going to be testing this as the p-value. So p-value is used to estimate statistical significance, and statistical significance is really just determining whether the differences we observed in the sample were actually due to the actual differences in the population, or if they were just a fluke. So step 1 in hypothesis testing is writing hypotheses. So each hypothesis test has 2 hypotheses. So it has a null hypothesis and an alternative hypothesis. Your null hypothesis states that there is not a difference in the population or the populations, and your alternative hypothesis states that there is a difference in the population. So there's 3 things we need to know before we start writing our hypotheses. So we first need to know the parameter we're testing. If we're testing a single proportion, a single mean, difference in means, difference in proportions, we need to know which one we're testing. Second, we need to know the direction of our test. So this will go into our alternative hypothesis, so whether we're doing non-directional, right-tailed, or left-tailed. Third, we need to know the value of the hypothesized parameter. So this is the number that goes into our hypothesized statements that you see. The null hypothesis is equal to 100, for example. And then just make sure that you know that the null and alternative hypotheses are always written in terms of population parameters. So if you need a refresh on what the population parameters are, you can go back to the first slide that I showed in the beginning around lesson 1. I think it had the chart with the population parameters and the symbols. So you always want to make sure that you're using those for the hypotheses. So here's just an example of writing hypotheses. The question is the average IQ score of all World Campus at 200 students higher than the national average of 100? So for our null hypothesis, we have our mean, because we're testing the average. Is our mean equal to 100? 100 is our hypothesized parameter here, because that's the national average that we're comparing our data to. Then moving into our alternative hypothesis, we still have the mean there, and we are doing a right-tailed test because we're seeing if the average IQ score of the students is higher than the national average. So it would be right-tailed. And then we have the same hypothesized parameter of 100. Okay, so randomization procedures. So you just want to know that when you construct a sampling distribution, you use that to make inferences about the population as a whole. So you construct these distributions given that the null hypothesis is true. So we say, so what that means is, given that the null hypothesis is true, we state that there is no difference in the population. So you can use your randomization distribution to find the p-value. And once you find the p-value, you can decide whether you should reject or fail to reject the null hypothesis. So just make sure that you know that you never accept the null hypothesis. You always conclude in terms of the null hypothesis and not the alternative hypothesis. And then you can just state a real-world conclusion after you decide whether to reject or fail to reject, putting that decision into the context of the original research question. Okay, so moving into p-values. P-values is how likely our sample proportion is given that our null hypothesis is true. So we compare the p-value to alpha. Typically our alpha is 0.05 unless otherwise stated. If you are not given an alpha level, you can assume that it's 0.05. So if your p-value is greater than alpha, then we can fail to reject the null hypothesis. Basically, when we do that, we can say that there is no sufficient evidence to say that there is something going on. On the other hand, if our p-value is less than or equal to alpha, we can reject the null hypothesis. So when we do that, we say that there is a difference in the population here. And just noting that a p-value less than alpha means that it is statistically significant. Okay, so on to our review. Do the majority of all World Campus Stat 200 students own a dog? What is the correct null hypothesis for this research question? All right, so our answer here is B. I did not change this. but I got this wrong in the last one. I don't know why I put D, but the answer is B here. I'm sorry. That's kind of confusing, but the answer is B. I somehow put the completely wrong option. It is wrong in every way for this question, but yes, so B is our answer here. Null hypothesis is equal to P equals 0.50. We're using 0.50 here because it's asking about the majority of Stat 200 students, so that would just be greater than 50%. Since we're using proportion here, you want to make sure that you're using the population parameter, which is P and not P hat. And then just making sure you're using that equal sign instead of, yes, it is a right-tailed test, but we're not going to use that here since we're looking for the null hypothesis. If we're looking for the alternative hypothesis, then C would be our answer. All right, let me just clear these. Okay. So we use Stacky to construct a sampling distribution based on a research question. We get a p-value of 0.06. What is our first conclusion in terms of hypotheses? All right, our answer here is C. So since our p-value is greater than 0.05, that means our data is not statistically significant. So we should fail to reject the null hypothesis. If our p-value is less than or equal to 0.05, then we would fail to reject the null. Then we would reject the null. Sorry. Yeah, so C is our answer. All right. Is the mean height in the population of all World Campus Stat 200 students different from 65 inches? What will we use in this scenario? Okay, so our answer here is B. So first, I'm going to start with the parameter that we're testing here. So we're looking for a mean. I think all of you got that part. So is the mean height of the population of students different from 65 inches? So it says mean in the research question, so that's a very big hint that we're using a single mean here. So A and D are both out. So now we're down to B and C. So how do we decide whether this is hypothesis testing or confidence interval? So we can tell that this is hypothesis testing because we have a research question here. And it's asking us to test, is the mean height different from, the Stat 200 students different from 65 inches? So we're testing the difference here, and then we're going to get a conclusion, and we're going to have to decide if it is or if it isn't. A confidence interval would be more of making an estimate of the mean height of the Stat 200 students if we were looking for it. All right, so now we're moving on to lesson 6. This is our last lesson. All right, so we're going to start with type 1 and type 2 errors. So you guys know that I'm going to start from the beginning of the hypothesis testing. So when you're conducting a hypothesis test, there are two possible decisions at the end of your test. So you can either reject the null hypothesis or you can fail to reject the null hypothesis. So in most cases, in terms of just testing data, we actually don't know if our decision is correct or incorrect in real life. We're just estimating based on what we got in our data. So if you decide to reject the null hypothesis, in real life, there really could be a difference in the population, which is the correct decision we made. Or there could really not be a difference in the population, but our sample just happened to be different. So that means that there is an error made. So, or on the other hand, if you fail to reject the null hypothesis is really true and there actually is no difference in the population, which is what we determined, that could be the correct decision that we made. So good. Or there actually is a difference in the population, but we failed to reject it. Another error was made. So there are two errors present here, and these are type 1 and type 2 errors. So type 1 error is when you reject the null hypothesis when the null hypothesis is really true. This is denoted by alpha, and your alpha is just your probability of a type 1 error. A type 2 error is when you fail to reject the null hypothesis when the null hypothesis is really false. So this is denoted by beta, and then beta is just the probability of a type 2 error. So the chart I have below is just summarizing what I said before in the previous slide. So you have two items here, what you decide and then what is actually reality. So your decision could be different or the same from reality. If your decision is the same as reality, agrees with it, then you made the correct decision. If your decision disagrees with reality, then there is an error made. And that's where the type 1 error and type 2 errors come to play. So this next slide should give you a more relatable example of a type 1 and type 2 error. So a man goes to trial where he is tried for stealing from a store. The hypotheses tested are the null is that he is not guilty, and the alternative is that he is guilty. So a type 1 error is committed here if we reject the null when the null is true. So here it means that the man did not steal from the store, but he is found guilty and is punished for a crime that he did not commit. On the other hand, a type 2 error is committed if we fail to reject the null hypothesis when it is false. So in this case, it means that the man did steal from the store, but he is found not guilty and he is not punished for a crime he did commit. So we're moving on to power, moving away from that for a second. So power is the probability of rejecting the null hypothesis, given the null hypothesis is false. So in other words, it's the probability of correctly rejecting the null hypothesis. So you can calculate power by taking 1 minus beta. And remember, beta is the probability of committing a type 2 error. Okay, so that was a lot, but we're going to go into our last review questions here. A group of culinary arts students is comparing two methods for preparing asparagus, traditional steaming and a new frying method. They want to know if patrons of their school restaurant prefer the new frying method over the traditional steaming method. A sample of people are given asparagus prepared using each method and asked to select their preference. A statistical analysis is performed to determine if more than 50% of participants prefer the new frying method. And here below we have our null and alternative hypotheses, and just ask which of the following is true. Okay, so our answer here is C, population proportion is being tested. So starting from A to B, This is not a left-tailed test because you see in our alternative hypothesis, it is right-tailed. And then going to B, there is not a type 1 error present because we haven't made a decision yet. So if we made a decision and then found out what was true or what was actual reality, then we would know whether a type 1 error is present or not. But population proportion is being tested here because we have P's in the null and alternative hypotheses. All right, so I think this is the last question. In the previous question, we stated that we should reject the null hypothesis. Suppose we reject the null hypothesis, but actually the patrons of the school restaurant do not prefer the new frying method over the old frying method. Which of the following is true? Great job, guys. A is our answer here. This is a type 1 error because we rejected the null hypothesis when the null hypothesis was actually true. So there is no difference in the two. A type 2 error would be present here if we actually decided initially to fail to reject the null hypothesis. So we didn't switch, but actually they did prefer the new frying over the old frying. So that would be an example of a type 2 error here.